All right, so lesson 13 is on graphs of rational functions. So rational functions are functions that look like fractions. So you're going to have something with x on top, you're going to have something with x on the bottom. So it's a function that can be written in the form where you have some kind of numerator and some kind of denominator, and those are polynomials. It says, remember that the domain of the rational function is a set of all real numbers that do not make the denominator equal to 0. So you always need to consider where your vertical asymptotes or holes are. So it says, find the domain of each rational function. So the first thing we do is we say, well, what if that denominator was equal to 0? Whoops, I don't know what I just did there. So if I set my denominator equal to 0, I would get x equals 0. So that is not in the domain. Okay, so x equals 0 is not possible. So our domain then, the easiest way to write it is just to say x is not equal to 0. You could also write it in interval notation, but it'd be a little bit different. It would be negative infinity to 0, parenthesis, union 0 to infinity. So basically you skip over the 0 because you don't have a bracket for either one. So you could write it like that as well. All right, so the next one, if I set my denominator equal to 0, I'm going to factor. So I get x equals 1 and I get x equals negative 4. So those are the values that we are not allowed to have for x. If we plug in 1 or if we plug in negative 4, we end up getting 0 on the denominator. That's bad. So those end up being either vertical asymptotes or holes or something. So for our domain, we just say x is not equal to 1, x is not equal to negative 4. That is the easiest way. If you did this one in interval notation, it would be really messy. It would be negative infinity to negative 4, parenthesis, union, negative 4 to 1, parenthesis, union, 1 to infinity, right? So you have to skip over negative 4 and also 1. So see how it's much easier just to say x is not equal to. All right, so sometimes they could be vertical asymptotes, sometimes they could be holes. Do you guys remember when something is a hole? What makes it a hole? If it factored in the numerator and denominator. So if I had like x plus 2 in the top and x plus 2 in the bottom when I factored and they canceled out, that is a hole. It is not a vertical asymptote. So vertical asymptotes, it says the line x equals a is a vertical asymptote if a is not in the domain. In other words, it makes the denominator 0. But we also need to say, and x equals a is not a hole. So I should have really put that in there. All right, so we're gonna factor the denominator. So if I have 2x squared minus 5x minus 3, this is kind of a tricky one. We have 2x and x, definitely.
2x minus 3, like 2x plus 1 x minus 3.
All right, so we think this plus 1 and minus 3. Do we agree? So look at your outer and your inner. All right, we get negative 6 and positive 1. It works. Do we still multiply and get negative 3? Yes. So a lot of people mess up on that one because they will make the signs the same, but they'll put 3 and 1 in opposite positions, and they're like, oh, but it still makes 5. But then if your signs are the same, they're not multiplied to be negative 3, so be very careful. All right, so we get x equals negative 1/2, and we get x equals 3 when we set each one equal to 0. Those are both vertical asymptotes, so both of those would work. So this might be one where there's like, the 2 vertical asymptotes, and you can graph it on your calculator and see. And maybe we have something like that, and then something like that. Do you remember those? What do you mean ignore the rest? Well, the negative 2 will be important. It ends up the u actually goes downwards because of that. But. All right, anyway, horizontal asymptotes. So the line y equals b is a horizontal asymptote. If as x goes to infinity, y goes to a certain value. All right, so there are 2 ways to compute horizontal asymptotes, the long way and the short way, right? We like the shortcut. I taught you the shortcut last year. But we're also going to talk about the long method and why that works. Okay, so I'm going to show you the long way. I'm going to discuss why it works, the way it works, and then we'll talk about the short method. Okay? So it says find the horizontal asymptote for f of x equals 10x squared minus 2x plus 15 all over 5x squared plus 3. So it says, in the long way, it says look for your largest degree in either the numerator or the denominator. Okay, so our largest degree is x squared. Okay, so what we're going to do for the long way is we're going to take every single term and we're going to divide by an x squared. See why it's annoying on the long way? Got a lot of writing. Okay, and we reduce out each individual term. So when I have 10x squared over an x squared, I get 10. If I have minus 2x over x squared, I get 2 over x. Then I have plus 15 over x squared. All over 5 plus 3 over x squared. Okay, so what we're doing with a horizontal asymptote is we're looking at the end behavior. We're saying what happens as x gets huge. As x goes really, really far to the right side, what y value I get closer and closer to. So it's saying, like, on the ends of the graph, what are you getting closer to? Is it going up to infinity? Is it going down to negative infinity? Is it going to a number? Okay. And then it's also saying, well, what happens as x gets really, really small? As x goes to negative infinity, are we going up? Are we going down? Are we going along a certain number? Okay. So really the way that we do this is we use what we call limits. So remember, we already have used this notation before. And we're basically saying, well, what's the limit as x goes to a really big number? And so each time you're taking the limit as x goes to a really big number. So let's think about each individual thing. Okay, 10 is just 10. Doesn't matter if x is big or small. All right, what about 2 over x? So what if I take 2 divided by 10? What do I get? 2 divided by 10 is 1/5. What about 2 over 100?
1/50.
1 over 50, smaller, right? 2 over 1,000, even smaller. 2 over 1 billion, really, really small. Super small. Do you guys understand that? I always relate it to something really gross. I'm going to share this. When you talk about fraction, you always talk about pizza, right? So if you talk about, oh, I have 2 pizzas, I'm going to divide by 10 people, you're like, I'm only getting 1/5 of a pizza. You know, you can do all that with pizzas. We always do when we're in elementary school. We always talk about pizzas. So what if you have 2 pizzas and you divide by 1 billion people? Are you getting pizza? No, it's like you're licking the pizza and passing it on. It's really sick, right? It's disgusting. You're not getting really any pizza. It goes to 0. Does that make sense? Do you guys understand that? So as I plug in a really, really huge number, this goes away. It goes to 0. Because 2 over a huge number, infinity, is 0. Same thing here. 15 over infinity squared, still 0. 3 over infinity squared, 0. So what are we left with? 10 over 5. And what is 10 over 5? It's 2. So that is the horizontal asymptote. That's saying as we get closer to infinity, we're getting closer and closer to 2. So you might be coming from above, or you might be coming from below. We're not sure. That's when we have to graph some other things to figure it out. But we're getting closer to that y equals 2. Do you understand?
Wait,
Why
Why did I just cross them out? Because as you're plugging in a huge, huge number, they go away. Right? 2 over a huge number is 0. Right? Does that make sense? So they're insignificant. They don't matter. All right, that is the long way. It's involving limits. That's why we can just cross this out. And the same thing happens, you can make this negative infinity. If I make it negative infinity, again, 2 over negative infinity is still 0, right? It still is just 10 over 5, which ends up being 2. So it doesn't matter if you do positive infinity or negative infinity, you get exactly the same thing. There are some that we do in calculus that go to different things. There are a couple of functions that do have a horizontal asymptotes that are different numbers, which is kind of strange, but usually they involve absolute values or something like that. All right, so the shortcut, remember the shortcut from last year? It's basically taking this long method and it's like getting rid of half the steps. It's just saying, oh, we know why that happens. We've done the long method before. We don't need to do it every time. So you look for your largest degree. So if you had 10x squared minus 2x plus 15 all over 5x squared plus 3, your largest degree is x squared. And you have it in both the top and the bottom. And we know that any other degree that's less than it will end up going away when we divide by x squared, right? So we cross them out. They're gone. So we do 10x squared over 5x squared. And we end up getting 2. Much easier, right? So you don't have to write all that mess. You can just say, oh, it's this. So when I see something like number 2, find the horizontal asymptote. So, well, this first one was y equals 2. So if it says find the horizontal asymptote for f of x equals 2x squared plus 50 over 4x cubed minus x minus 1. What's the largest degree? X cubed. Do you have an x cubed in the top? No. Do you remember what we do? We write in the x cubed. We circle those two things. We ignore everything else. 0 over 4? 0. So y equals 0 is our horizontal asymptote. That's a very common one. It's often y equals 0. All right, how about something like this? Our largest degree is x to the 5th. Do I have an x to the 5th in the bottom? No, so I write it in, x to the 5th. See, I'm doing less and less steps every single time. Really shortcutting the shortcut. So I have 2 over 0. What is that? It's undefined. What does that mean about our graph? No horizontal asymptote. That's what it means. There's not one. It's just one where they're either going to go both to infinity, both to negative infinity, or they're going to do the little John Travolta, going opposite directions. Okay? So their ends are going to one of the infinities. All right, so slant asymptotes. Do you remember these? All right, sometimes you don't have a vertical asymptote or a horizontal asymptote. Sometimes it is a slanted line that you're getting closer to. So maybe I have a vertical and I have a slanted asymptote, and it looks like this. You can have graphs that look like that. It's kind of crazy. It goes along the slanted line. So this will happen when the degree of the numerator is exactly 1 more than the degree of the denominator. So as I look at number 1, it says find the slant asymptote for this function, and I notice that I have x squared on top. The degree on top is 2. And the degree on the bottom is only 1. So because of that, if I was finding the horizontal asymptote, what will happen every time I have a slant asymptote? I have 1x squared plus 5x plus 4 all over 0x squared plus x minus 3. What happens? There is none, right? So when that happens, when you get no horizontal asymptote, look for a slant asymptote. Is our degree exactly 1 more on top than it is on the bottom? Mm-hmm. Yeah, it's 2 instead of 1, right? So it's 1 more on top than it is on the bottom. So because of that, if I do long division, I end up getting a line. So to find the slant asymptote, use long division. So we know how to do this. So we say, what do we multiply x by in order to get x squared? So we need an x. X times x is x squared. X times negative 3 is negative 3x. Draw the line, change the signs, add straight down. Repeat the process. X times what gives you 8x? We need an 8. 8x minus 24. Draw the line, change the signs. Add straight down. We get 28. It does not matter what your remainder is. What does matter is right here. That's your slant asymptote. So our slant asymptote, we write it as a line. Y equals x plus 8. There's no horizontal, and you notice that it's 1 degree more on top than it is on the bottom.
So if it was like 30 cubed on top and no exponent on the bottom, this would not work.
Right. So let's do a little bit more with this. So how about the vertical asymptote? Where's our vertical asymptote? X equals 3. Set your denominator equal to 0, right? So we have x equals 3. And we have y equals x plus 8. So go up 1, 2, 3, 4, 5, 6, 7, 8. And then we have our slope, our slant asymptote. I'm running into my writing. And then we pick one of the sides. So you remember what we did before is once we had all the asymptotes drawn in, we just picked a couple points. So if you plug in 0 into your original, what do you get when you plug in 0? Like you do a little t-table and you plug in 0 into this original. Negative 4 over 3, right? So it's going to be somewhere around here. All right? What happens when I plug in something to the right of the vertical asymptote, like 4? It's a little bit harder. I'm going to go ahead and graph so you guys can see in the end what it looks like. So I'll do this little thing. Go ahead and get your calculators out and do it along with me too.
Okay, y equals 0 gets negative 4. Oh, no.
Okay, so I'm going to put the numerator. I'm going to put it all in parentheses. So I'm going to do a numerator. So x squared plus 5x plus 4. And then I'm going to divide by the denominator, which was x minus 3. Okay. You could always do a t-table on your calculator. So you could go to second table. So if you didn't know these values, you can put things in. Remember, I've already changed yours, so we've gone through the whole table set, making it so you can ask, right? But if you haven't done that, make sure you do that. So you can put in whatever value. So if I wanted to put in, like, I just put in 0, right? Right, that's negative 4/3, negative 1.33333. Right, if I put in 4, what do I get? 40. It's way up there. So if I plug in 4, I'm getting 40. So it's way up here. But that's enough to know that we are on this side of the X shape. Do you guys see? So it's going to look like that. So that's all I needed to know. I just need to know, like, what side of the two X, like, when I make the X, which sides I'm on. Does that make sense? And it's still a function. It passes the vertical line test, so I know I'm good. So if you graph it, so if I hit graph, you're probably not going to see the whole thing. I'm graphing the whole function. Did you see me put that all in? Numerator, denominator, the whole thing. All right, so when I graph it, I do see part of it, but I don't see all of it. That's why it's kind of important to know how to do this by hand, too, so you know you're missing part of it. So we're going to go up to a y max of, we know that one number was 40, right? So let's go up to, like, 60. And hit graph. Just like that. Does that make sense? And if I went over further along the X, I think you would definitely see the, let's say I do negative 20 to 20. I think you'll see that vertical, or that slant asymptote a little bit better. So it's drawing it in, drawing the other one in. All right, the slant asymptote is this line right here that it's along. The vertical asymptote was the line right here that it's along. Does that make sense? Do you guys understand that? Okay. All right, so let's do a little bit more. All right, holes. So it says holes. Sometimes there are values that make the denominator equal to 0, but they can be canceled when we factor the numerator and the denominator. Since we still can't input the original into, or input this value into the original function, there's a hole. Do you guys remember the hole thing? Okay, so this should be pretty easy then. So as we factor, we're going to factor into x plus 2 and x minus 2. And we notice that on the bottom, we have an x minus 2 as well. So the entire x minus 2 cancels. So when we do that, we're left with x plus 2. So our simplified function, that's the one we're going to graph. Our simplified function is y equals x plus 2. Because we canceled the x minus 2, there's a hole at x equals what? 2. It's what made it 0 over 0. So at x equals 2. See how if you plug in 2, you'd have 0 over 0? So we graph y equals x plus 2 just like we know how to graph it. It's a line, right? Y equals mx plus b. So we have y equals x plus 2. We have the y-intercept of 2. We go up 1, right 1, up 1, right 1, up 1, right 1. You could do down 1, left 1, right? So we get this nice straight line. So the last thing that we need to do is we need to realize that there is a hole at 2. So go over to x equals 2 and always find where it's matching up on your graph. A lot of you guys did this last year. You just drew a hole on the x-axis, and I was like, not exactly, right? It's where it matches up on the graph. So it's at that point right there. That's where your hole is. So there should be, it should kind of skip over that point. So it should look like that. Does that make sense? All right, now you don't always get lines. Sometimes your simplified function is like 1 over x plus 2, right? If you have 1 over x plus 2, then it's something that has asymptotes, right? Vertical asymptote, horizontal, you'd have to find it. All right, so steps for graphing a rational function. So we go through all these steps. We find the vertical asymptotes, the horizontal asymptotes, we find the x-intercepts, the y-intercepts. We find any slant asymptotes if we have them, and then we use t-tables to find any additional points if needed. Okay, usually just on the right and left of the vertical asymptotes. All right, so we're going to go and do this one. So it says sketch the graph of f of x equals 3x squared minus 12 all over x squared minus 2x minus 3. So the first thing we always do is we always factor. So I'm going to pull out the 3. When I do that, I have x squared minus 4. And when I factor the bottom, I have x minus 3 times x plus 1. So the top factors into 3 times x plus 2 times x minus 2 all over x minus 3 times x plus 1. So there's a lot going on here. Do we have any holes?
No.
We do not have any holes, right? So no holes. How about the vertical asymptote? Are there, well, there's more than one, but vertical asymptotes.
3 and -1.
Right, we set our denominators equal to 0, so we get x equals 3 and we get x equals -1. All right, our horizontal asymptote, I always look at the original for that one. So when I'm looking at 3x squared minus 12 all over x squared minus 2x minus 3, 3x squared over 1x squared, what do I get? 3. So that's y equals 3. So let's sketch these in. So I have x equals 3, which is a vertical line, right? Vertical asymptote. And I have x equals -1. And then I have y equals 3. So it's one of those H shapes. Those are the hard ones, right? You don't like those as much. All right, now we also want to find X and Y-intercepts if possible. Sometimes they don't exist, sometimes they do. So let's find it. So X-intercept. How do I find an X-intercept? Plug in 0 for Y. So we're going to have 0 equals 3x squared minus 12 all over x squared minus 2x minus 3. Basically what happens is that whole denominator is pointless, right? You can multiply it over, it all goes away. You're really just worried about setting your factored form, right? If you simplified it, setting your numerator equal to 0. So really what we're going to do for the x-intercept is we're going to set the simplified numerator equal to 0. Okay, so that's the quickest thing to do, because you're going to set the denominator equal to 0 to find the vertical asymptote. You set the numerator equal to 0 to find the x-intercept. So we're going to have 3 times x plus 2 times x minus 2 equals 0. So we get x equals -2 and x equals 2. Now I always warn you guys, don't write these like x equals 2 and x equals -2, because when you do, people think they're vertical asymptotes. Write them as points. It's 2, 0 and -2, 0. So we're here and we're here. All right, next up, y-intercept. This is the easy one. You plug in 0 for the x. So you can plug it into the simplified form or the original. The original is usually the easiest. If I plug in 0, I get 3 times 0 squared minus 12. You can usually do it in your head. Do you guys see? I don't have to write all this. I'm just doing it for your notes. What do we get? -12 over -3? 4. So that's the point, 0, 4. Can you see that you're crossing the horizontal asymptote? That is okay. Horizontal asymptotes, the only time you're not crossing it is on the ends of the graph. You can cross it in the middle. You can also cross them here, which is kind of weird when that happens, but you can. You can cross it kind of like on the left or right side of the asymptote. All right, so we're going to have this. So we're going to have some kind of like cubic function in the middle. We had 2 points that helped us to draw. All right, now that we have this point on the left of the first vertical asymptote, what do you guys think it's going to do on the left side? It's got to go along here, and it's got to go along here, right?
So they can't cross horizontal, but not vertical.
They cannot cross vertical asymptotes. Because think about it, if you're crossing a vertical asymptote, that means that a point exists at the vertical asymptote, but we know x can't be that number, right? X is not allowed to be -1, so we can't have a point on it. So the last thing we need to do is figure out what's happening on the right side of our graph. So see, it's a function, it's passing the vertical line test. So as I do vertical lines through here, it's passing the vertical line test, but I don't have anything over here yet. I need to figure out what it's doing over here. So I'm going to plug in something on the right of the vertical asymptote. So what should I plug in? Let's try plug in 4. Plug it in directly on the right. So it was at 3, so plug in 4. So if I plug in 4, I can plug it into any version. I can plug it into the original or the simplified version. So let's say I plug it into the 3 times 4 plus 2 is 6, 4 minus 2 is 2, all over 1 times 5. So what do we get? 36 over 5. What's that as a decimal?
6.2.
Yeah, so 6 point something. 7.2, yeah. So we're going to go up to 7.2. So 4, 1, 2, 3, 4, 5, 6, 7.2. All that matters is that we know it's above that vertical asymptote. So because of that, we know it goes along the vertical and along the horizontal, so we just kind of connect it, right? So it looks like that. At the very end, were there any holes? Nope, so we're good. That's your graph. So one thing at a time. Go very slowly on these. You guys are going to be much better at these this year than you were last year. I know you didn't like them in Algebra 2. That's why we preview everything in Algebra 2, so when you see it in Precalc, you're like, oh, this makes total sense now. Don't you hate that when you're like, man, I wish I would have known this last year. All right, so next one. So it says sketch the graph of f of x equals x minus 1 over 9 minus x squared. All right, so we're going to have f of x equals x minus 1 over 9 minus x squared is going to be 3 minus x times 3 plus x. It's the difference of two squares. Any holes? Nope. No holes. All right, let's start with vertical asymptotes. What do we got? We do 3 minus x equals 0 and 3 plus x equals 0.
-3.
So we get -3 and 3. Horizontal asymptote, look at the original. We had x minus 1 over 9 minus an x squared. So we have -1 x squared and we have plus 0 x squared. So 0 over a -1 is 0. So we have y equals 0. So let's draw in our asymptotes. It's always hard when you have to go on top of one of the axes. Colored pencils help. All right, and then -3. And then 3. All right, so we want to find x-intercepts, y-intercepts. We'll do the easy one first. Let's do y-intercept. Plug in 0 for x. So we have 0 minus 1 over 9 minus 0. -1, 9. So we have 0, comma, -1, 9. So we're just slightly below the x-axis. But it can cross. We don't know exactly what's happening in there. How about x-intercepts? So if I plug in 0 for y, I get 0 equals x minus 1 over 9 minus x squared. Remember, the denominator doesn't matter. If you have 0 equals a fraction, it's always the numerator that matters. You can imagine multiplying the denominator over, it goes away. You can think of it that way. Yeah, so we have x equals 1, which is the point, 1 comma 0. So we have that. So it's crossing that horizontal. I know you guys don't like when that happens. It does. It crosses. Now, there is a lot of missing information here. We do not know what's going on, right? We can't tell. If you had your calculator, you could just graph it, but the whole point is knowing how to graph this without using your calculator. So let's plug in some points that will be useful to us. So we definitely want to plug in things that are near the vertical asymptotes, okay? So that will tell us whether we're above or below the horizontal. So let's plug in, you really like 5, don't you? I'm going to plug in -4 and -2. Wait, I don't know why I did -2 there. -4 and -2. And I'm also going to plug in 2 and 4. Because I want things on each side, here, 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 and there. Each side.
Why did you do -2? Oh, because it's on the other side of 3.
Yeah. All right, so let's say I plug in -4. So I get -4 minus 1 over 9 minus 16. So I get -5 over -7. I get 5 over 7. So not quite 1. So I'm going to have -4, comma, almost 1. Okay, like that. Then I try -2. So if I have -2, I get -3 over 9 minus 4, so 5. So -3/5. So down there. You see it? It's hard with the -1/9 and -1/9 is actually a little bit closer. All right, and then if I plug in 2, I get, let's see, 2 minus 1 is 1 over 9 minus 4 is 5, so I get 1/5. And the last step, if I plug in 4, I get 3 over 9 minus 16, so -7, so -3/7. So this one was a lot that we had to do. Okay, do we have enough information? Yes. So in the middle, can you tell what it's doing? It's not a parabola. It's one of these. All right, it's kind of hard to draw because those are very close to the x-axis. It's very like flat in the middle. All right, and then on the left-hand side, we're going to go along the vertical. We're going to hit that point, and then we're going to go along the horizontal. And the other one we're going here. Whoops. Didn't mean to go down like that. Okay, so there. No holes, so we're done. Okay, so that's our graph. So just one thing at a time. Asymptotes, intercepts, extra points. Okay, always that pattern. Does that make sense? All right, any questions on that? If you did notice you had a slant asymptote, you'd have to do the long division, right? I mean, lots of steps.